project, we used the A-star algorithm as heuristic search, value iteration, and step reinforcement learning to decide the different actions our agents will take. Since A-star algorithm is a simple way to find the shortest path to a particular goal in a considerably short amount of time, this is our first path search algorithm in different situations. We have used value iteration to spread the rewards throughout the grid. To make more complex decisions, we used three-step reinforcement learning in situations where opponents are jeopardizing our possible actions. Our attacking agent will choose its actions based first in whether it can observe the enemy or not, and whether the enemy is scared or not. If our agent doesn't sense the presence of enemy, it first will look for the best path to reach food or capsules. Every time our agent has eaten 4 foods, it will try to come back home to ensure the scores of those foods. If our agent is being chased by our opponent while being in enemy territory, it will immediately try to find the best path to escape. A queue table is built for this purpose. In case the enemy is scared, our agent will not run away if it is nearby. Instead, it will try to find the best path to eat all food and capsules he can in that period of time. On the other hand, our defending agent has the following approaches. From the start position, it will go towards the border area through the path given by the A-star algorithm. Here, the goals are the different entry points of the maze. Once it reaches the border, it will start patrolling until an opponent is detected in our sight. Our defending agent could detect enemy in two ways: when enemy is within 5 Manhattan distance range, or when our amount of food decreases. In this case, our agent will try to get to the area where the last food was eaten. It will then hunt the enemy using A-star algorithm. Some challenges have been found during the implementation of this solution. In mazes, our attack agent found itself in a situation of stalemate while trying to enter enemy's site if the possible entry points are being covered by opponent's defender. In a similar way, when trying to go back home and an enemy was found in our way, in some mazes our agent found himself trying the same set of actions repeatedly. At that point, the agent was only choosing actions based on A-star algorithm. Our defend agent is not able to predict the path that the enemy is going to take. The following improvements have been made. Within enemy territory, the A-star path to your enemies are marked with negative rewards. In certain scenarios, the best way to escape might also lead us closer to the opponent. To ensure not to discard this path, big negative rewards are given to nodes closer to the opponent in a range n-1 divided by 2. Thus, our queue table is updated through value iteration. After estimating the future discounted rewards, we look at the next 3 steps ahead for the reward and decide for the path that leads us to the maximum return. This ensures that we do not choose an action that gives us a big immediate reward but poor reward afterwards. In our queue table, a reward of 70 is given to the entry points and a discount factor of 0.91 so that even if our agent is far from them, it will still have a path that is positive values leading to the exit points. In points surrounded by walls, the rewards decrease quickly. Throughout the project, a variety of methods were analyzed, considering the different scenarios that our agents could be exposed to, as well as the basic condition of, or limitations like time and the rules of the tournament itself. Thus, the selected techniques were tested and adjusted iteratively based on the different daily results.